Thank you very much. Yeah, and thank you very much for the invitation to come here. Um, I had been in Florence a really long time ago when I was still actually a student, I think. So this is a completely different kind of memory. um, so actually, since it's always hard to predict sort of the background of the people that come and listen to these talks. Um, Maybe can I know, so who of you does not have like a standard HepTH background? And I know well, at least one person. Okay, right, so we're all physicists here. Okay. Well, Marcus, that might mean that I make less comments about the elementary things. um, Yet I want to, so I wanted to make these lectures pedagogical as well. I'll try my best at least. And well, it might be that today is kind of an easy day for you, and that the lectures will evolve a bit more into more complicated stuff later on in the week. The goal of these lectures is to introduce some kind of new partition functions. For four-dimensional n equals 2 theory. And I'll say a little bit about what that means, particular for Marcus, in a bit. But what I want to say at first is that this will have connections with various other themes in the community. Well, first of all, let me start. This is very much related to quivers and stability conditions. And in particular, I'll make some remarks about sort of the physics background of all of this. So the DT invariants from a more geometric perspective. Well, quivers plus stability. So this is not necessarily what I'm going to talk about. I will take a slightly different approach, but that will be all very much related to this. There is a relation to things that are called non-perturbative topological strings. And also to this topological strings spectral theory, duality, that was discovered by Marcus Mourinho and Albert Grassi and Gu. Something else that will feature actually in the talks is so gauge theories and the so-called omega background. And well, mostly I'll explain you the important role of spectral networks, abelianization, and exact WKB analysis and all of this. So these are just a few sort of themes that these lectures that they relate to. And so what I want today, so the plan, so today I want to start with some introductions actually to four-dimensional n equals 2 theory, in particular Seiberg-Witten theory, also sort of the embedding of this in string theory, because that will all lead us to sort of this geometric picture of BPS states that we will need in the later half of this series of talks. Unless, of course, everyone is completely familiar with cyberquitting theory, in which case I'll have to make a jump. Who would appreciate hearing this? Well, actually, there's a fair amount of people. Okay, let me make a compromise there. Tomorrow I want to talk about spectral networks and BPS states. And in my last lecture, I want to talk about exact WKB and basically show how all the ingredients that we talked about at that point combine into this new partition function. Right. Yeah, so let me at least introduce, let me introduce all the notions from four-dimensional n equals 2 theories that will be important in the following. Right, so maybe just for Marcus, so we're talking here about a four-dimensional QFT with some extended supersymmetry. So that means, supersymmetry means you have supercharges. And in this case, we have two sets of supercharges labeled by this capital I is equal to 1 and 2. And so why do I write this down? So like a usual, well, right, so this is just meant to be a set of these supercharges. Now I look at their algebra. And so as you all know, the anticommutator, maybe I give this a bar to make it clear. The anticommutator of two of these supercharges is something proportional to a translation. So this is true for any superalgebra. In this case, because it's extended, because we have two copies of it, and just want to write this down here. Because we have two copies of this, we can also look at the anticommutator between two Q alphas. And that is proportional to something that is called the central charge. So this is an element in the supersymmetry algebra that commutes with all other elements. And it will later play a role as defining a stability condition on these moduli spaces, for instance, of quiver representations, or any other way of phrasing the BPS moduli spaces. So this is where it comes up, that stability condition. Something else that you'll probably know very well is that if you look at representations of this supersymmetry algebra, then, I mean, these representations, they're classified, or they're they're classified by some numbers, say, to each representation we can associate a mass, as well as the central charge. And for each representation, we have this inequality that the mass is always greater or equal than the absolute value of the central charge. Since I talk about BPS states, I need to introduce what that is. So a BPS state is such that it's a representation such that there is an equality between these two numbers. So the mass of that representation is equal to the absolute value of the central charge. That means that, well, let me actually write it as representation here. That means that this representation is half-dimensional, so it, compared to a generic representation. And that means that these BPS, that these kind of representations, that they're more stable in a different way against deformations. And that means that they're good objects to study, for instance, in the strongly coupled region, when we let the gauge coupling become large, because these BPS states cannot just fall apart into other, decompose into other BPS representations. Right. So what I want to review today is how such BPS representations, how they're represented in terms of geometry. And so to do that, I'll look at an example of an n equals 2 theory. Which is the Seiberg-Witten theory. Which, right, so this is a supersymmetric version of just a pure Escher-2 gauge theory. So there is no matter. That means that the Lagrangian of the theory can be built out of just one representation, namely the vector representation, or the vector multiplet as it's sometimes called, which contains a gauge field, a complex scalar, and then it contains two fermions. So if you write down the UV Lagrangian, the microscopic definition of this theory, we write it down just in terms of those fields. And they form a representation of this n equals 2 supersymmetry algebra. Right, let me write this down. So it turns out that this theory, that it's asymptotically free. So that means that so the gauge coupling G, you can compute that it will depend on the energy, which I will denote by a capital lambda, in a way that it decreases if the energy becomes larger. Right, so what we want to do is we want to describe how this theory looks at strong coupling. So that means that we need to look at low energies. And how do we start by finding out how a theory behaves at low energies? Well, we look at the potential term in this Lagrangian. And in this case, the potential term will be the commutator of phi and phi bar. Well, so maybe I should have said this. This is probably clear for most of you, but this is transforms in the adjoint representation of the gauge group, SU2. And this is a connection of an SU2 gauge bundle. Actually, let me write this down. So I can write down this invariant, that's a part of the Lagrangian. And well, looking at low energies means that we want to minimize this particular potential. Right. So minimizing this potential, so at least classically, it means just from the information that we have about the Lagrangian. So what does that mean? It means that phi needs to become diagonal. So this is the Pauli matrix. So it will have this diagonal form A and minus A, which means that the gauge symmetry SU2 is broken to a U1. So in the low energy description, we find that this SU2 gauge theory is broken to a U1. And we find that there is a modular space. So as Marcus said, whenever we have, so this A is a complex number. So whenever we have some continuous variable parameter around, then this defines as a modular space. And so in this case, it defines as what is called the Coulomb branch. Coulomb branch, which is the modular space that parametrizes all these vacua. But because of the Weil symmetry that we still have, we usually decide to parameterize this with a parameter that we call U, which is the trace of phi squared, maybe half. Right, so that's kind of the classical description. And so the whole, right. I feel a bit silly explaining this to most of you who already know this, maybe. But on the other hand, this is an amazing work, and so it deserves to be told as many times as possible. So, right. So the whole work of Seiberg and Witten was about finding out what happens quantum mechanically. So how is this theory, this SU2, pure SU2 gauge theory, how is it described in this low energy limit where the gauge symmetry breaks into a U1? And the reason that they could make progress here is exactly because of the supersymmetry. So the supersymmetry gives various constraints on what can happen in this low energy limit. First of all, so supersymmetry implies that this Coulomb branch, which is now just, well, a space parameterizing these U's, that it actually has a geometric structure, namely it's scalar. So let me maybe call this B. So it implies that this space that parameterizes these expectation values of this complex scalar, it's actually a Kähler manifold. And so its metric, its Kähler metric, can be written in the form, the imaginary part of some object which I will call tau IR and which I will define in a minute. And then, so the complex structure is given by A and A bar. There is another ingredient that I haven't told you about, namely how this central charge is realized in terms of the vacuum expectations values of this scalar. And so here we need to note that as well as the phi's, which give these, which are the electric Higgs potential, as it's called, there is also the magnetic version. So we could have also written down this theory equivalently in terms of magnetic variables. And in terms of the dual electromagnetic field, which is equal to star of F. So there is also a magnetic expectation value in the game. And the central charge, if you look at the structure of the supersymmetry algebra, you will find that the central charge can be written in the form P times A dual plus Q times A, where Q comma P is the electric magnetic charge. Of the representation. This is another invariant of any representation of this supersymmetry algebra. Right. So supersymmetry tells us something more. So we can consider now a bundle over the scalar manifold, the Coulomb branch, where the monotomies of this bundle define a lattice, the electromagnetic lattice, gamma, which is spanned by A and A dual. So, how to think about this? So maybe let's draw a picture. So in this pure SU2 case, this Coulomb branch is complex one-dimensional. We can parameterize it by U. And then at each point of this Coulomb branch, I can compute these variables, A and A dual, and they will define a lattice. So if I'm close to infinity, it will turn out that this electric coordinate A is very small, and A dual is large. Whereas if I'm more to the center of this Coulomb branch, then my A will be very large, and my A dual will be small. And there are singularities in this at this Coulomb branch. And if I go around these singularities, I will get non-trivial monotomies of this SP2Z bundle. Right. Well, I said that I could compute what A and A dual are. At this point, I can actually not do that yet. But I do know that if I'm in very far out on this Coulomb branch, where effectively the gauge coupling becomes small, that I can approximate this in terms of U. Maybe the square root of U. Sorry, I did this completely the wrong way around. Sorry. This is very silly. You should have corrected me. Wait. No, this is, well. No, sorry, this is true what I read. Yeah, let's leave this for a second. Sorry. You might think that A is very large because it grows as the square root of U, but actually there is, AD is even larger. So this is like the normalized picture. Sorry about that. Right, so AD and A, they're not independent variables. We could either describe the theory in terms of electric variables or in terms of magnetic variables, but they will have a relation. And supersymmetry tells us that this relation is holomorphic, so that A dual is a holomorphic function of A, and the way to encode that dependence, that's how the prepotential comes in. So F naught is called the prepotential. So one way to think about this is that this prepotential defines a holomorphic section of this SP2Z bundle over the Coulomb branch. And the metric that we wrote in this particular form can now be related to this prepotential as well. So this tau IR, as I call it, the IR gauge coupling. This is how it comes up in the action. So that will have the form of a second derivative of this prepotential. So the whole structure of supersymmetry effectively tells us what the geometry of this moduli space is, this Coulomb branch. And it tells us that this geometry can completely be encoded in this object F naught, which is called the prepotential. So now you might wonder, can we actually get exact formula for this prepotential, and can we determine exactly what this metric is over the whole Kähler moduli space? And so how do we determine? And so here we need to make, so we have two motivations. One is far out in the Coulomb branch on B. The theory behaves semi-classically. And hence, we can compute F naught just by our Feynman diagram and other QFT techniques. And so what you find if you do that, well, let me write it actually in terms of tau, in terms of this low energy coupling, the complexified low energy coupling. So that coupling will, to first approximation, just behave as the UV coupling. So tau naught is the coupling of the original theory that we started out with. So it can be written in terms of theta over pi plus 8 pi I over g squared. But then this coupling has a one loop correction, and it only has a one loop correction. And this one loop correction can be written in terms of our vacuum expectation value A in this particular way. And then there are general arguments that tell us that there can be instanton corrections. And these instanton corrections, we can determine the form of these, but they will have coefficients that at this point we cannot determine for n. Right. So we started out with pure SU2 theory. We looked at what happens at low energies. We discovered that there is this moduli space. We can compute what this, so the moduli space is completely determined in terms of this prepotential. We can compute what the prepotential is near infinity. So how do we proceed to find what the structure is on the whole space? And so this is the magic of Seiberg and Witten. Right, so remember that we had this sp2, bundle over this Coulomb branch. And using this form of F naught, we can determine what the monotomies of that sp2, bundle is at infinity. Because it's a Kähler metric, which needs to be positive definite, we can infer that there needs to be at least two other singularities. It's nothing. There is no possible solution with just two singularities. So at first, classically, you might think, well, where could these singularities be? Well, obviously, we've got a singularity at u going to infinity. So the monotomy given by form of the prepotential. And classically, you might think something special happens as well at the point u is equal to 0. Because remember that the expectation value of phi was proportional to a. So if a is 0, that means that this gauge symmetry SU2 is not actually broken to SU2 to U1. So it might be that this is another special point. But then, if you just assume that there are these two special points only, two singular points only, you get into trouble because your metric is not positive definite anymore. So the assumption that Seiberg and Witten made is that there are, in fact, two singularities. And so when they work that out, that turns out to be, in fact, a consistent setup. So the proposal is the following. So let's have two singularities, one at minus lambda squared and one at plus lambda squared. And then we have this singularity at infinity. So what they found is actually a characterization of this SP2, bundle, which is consistent with this picture. And right. And so what follows from that picture is that what happens at either of these 2 points is that one combination, so a combination at singularities, a given combination P times A dual plus Q times A is equal to 0. In other words, there is a BPS representation with these electromagnetic charges P and Q, which become 0 at these points. So this point we call the monopole point. So because that particular combination becomes 0, and then there is the other one, which is a diene. That's a combination with electric and magnetic charges. And so this solves some questions that you might have as a physicist, especially as a string theorist, because according to string theorists, there cannot be any singularities. The heuristic is that strings are kind of string-like, and they will not see any singularities. So you might be confused at first to see singularities popping up on this moduli space. Yet because of this logic, we have found that there are two of these BPS representations that become massless. This solves the riddle because we were not actually allowed. We have, by going to this low energy picture, we have implicitly integrated out lots of massive modes that were above the energy scale. Yeah, we shouldn't have done that because we have massless particles at these two vectora, at these two particular points. So we only see these singularities because we did not because we did not do we did not treat these particles appropriately. So this will be some logic that will come up a little bit later as well when we talk about hyperkähler metrics. So the other thing that Seiberg and Witten did is they translated all of this into a geometric picture. They noticed that the structure of this particular sp2, bundle over this moduli space is very much related to that of an elliptic curve. So H1 of some elliptic curve, which I denote by sigma. So it resembles a bundle whose structure group is the H1 of an elliptic curve over a certain moduli space of complex structures on this sigma. So we might think of this column branch as the modular space of complex structures on a given, on a special curve sigma. So this sigma is called the Seiberg-Witten curve. And for this SU2 theory, it has a very specific form. I will write it in a form that will be useful later, which is the so-called Kyoto form. But in this case, okay, well, should I do this? Okay. Yeah, let me do that. But let me do that maybe on a different part. Right. So this precise data of the Seiberg-Witten solution can be formulated in terms of a Seiberg-Witten curve, which is a genus 1 curve in this case with some punctures, and it can be written in this particular form. Where U is the parameter on this column branch. So at every point, so we've got a family of elliptic curves here They're labeled by U. U is the complex structure parameter of this curve. And so this elliptic curve, since it's elliptic, its one cycles form a two-dimensional lattice. And so, right, so let me write this down like this. So the one cycles are generated by, sorry. So they form a two-dimensional lattice. So we knew that this lattice was generated by these parameters A and A dual. And how do we get these A and A dual from this curve? Well, it turns out that we need to add some additional information, which is called the Seiberg-Witten differential. And in the way that I've written it, and that's why I've written it in this way, is that this differential has just to form W times dz. So this is a meromorphic one form. And I can integrate it along, well, I can take a period integral around any element in this two-dimensional lattice. And what I find, so if I take a particular basis of this two-dimensional lattice, so and I take a basis of an A cycle and a B cycle on this elliptic curve, then it turns out that I can identify, if I choose this in a particular radius basis, that this period along the A cycle reproduces A, and that the integral along the B cycle reproduces A dual. And indeed, since this curve is a function of U, of the place where we are on the Coulomb branch, these period integrals, they will in the end be functions of U as well. And by inverting these relations, I can then find the pre-potential as a function of A. And basically because there is a unique family of these Seiberg-Witten curves which has exactly the right structure of this sp2, z bundle over the Coulomb branch, this pre-potential is defined uniquely. Yes. Right. So the picture that we have is that there is, the geometric picture is now that we have the Coulomb branch, but now we can also see it as the modular space of, well, modular space of complex structures on sigma. At each point, so this point, this space is parameterized by U. So at each point of the space, we have a certain Seiberg-Witten curve, which if you convectify it is a genus zero curve. And what happens at these two special points, at these two singularities, is that well, a combination of periods will go to 0. That's how we describe these singularities. So in terms of the geometry, that means that there is a cycle which goes to 0 size. And I don't worry about punctures here for a second. So that's the important picture of the cyberquitten geometry. And so these monotomies that we talked about previously, they can now be seen as Picard-Lefschetz monotomies of this Riemann surface sigma. Right. Is that clear for those of you who didn't hear it before? Hopefully it's still clear for those of you who did hear it before. But yeah, I wanted to make this connection between the physics of n=2 theories and geometry. So what we want to do next, and what I want to explain in more detail tomorrow, is we want to find, well, so we have found some BPS states appearing in this story. We found this monopole and we found a dion whose central charge, or equivalently mass, is equal to 0 at these singularities. But you might ask, can we now find all BPS states? In this theory. And so one thing that's good to remember is that because we're asking a question about BPS representations, these BPS representations, they were, well, not sensitive to small deformations. So this implies that this spectrum of BPS states, the collection of these BPS states, is invariant as well under small deformations. And what do I mean by a deformation here? For instance, a deformation of the complex structure on this cyberquitten curve. So what we find is that, well, what should be the case is that if you just move a little bit in this modular space, then this BPS spectrum should be the same. On the other hand, BPS states they may form bound states, or they may decay when the argument of the first BPS state and the argument of the second BPS state is the same, right? So we have the triangle equality. We need that BPS states satisfy mass is equal to the absolute value of the central charge. So the only way to have two BPS states recombine into another BPS state is that the arguments of these central charges, that they need to be the same. Well, that's a real codimension 1 condition. So now that we know how to express the central charge in terms of A and A dual, and we can actually compute what the central charge is in terms of U, we can draw this region where BPS states are allowed to form bound states or decay. We can form this, we can draw this on this Coulomb branch, and we find that it's some closed curve, looks like ellipsoid, which intersects these two singularities, where obviously the arguments of so this is the locus where the argument of A is equal to the argument of A dual. So what we find is that this modular space splits up into two regions. This region and the region outside of this curve. So this locus is called the wall of marginal stability. So that's where these BPS states are allowed to join bound states or decay. And so outside, well, maybe I should take a new color. Outside of this wall of marginal stability, we have the so-called weakly coupled region. That's where that's where the theory behaves semi-classically. And then inside this region, we have a strongly coupled. So basically, we've reduced the problem now to finding the spectrum, spectrum of BPS states in any vacuum outside of the wall of marginal stability and in any point of this chamber inside the wall of marginal stability. So let's see. Right, so I want to make a connection as well of these BPS states to Donaldson-Thomas invariants. And I want to give an introduction that will finally lead us to this method of spectral networks of finding the whole spectrum of BPS states. And this is all motivated by that string theory picture. There's again the question, where should I start? Right, so this is the story of geometric engineering. So I often try to explain some of these things to pure mathematicians that are interested in these things. And I would explain them in a completely different way. But since most of you are physicists, you're probably already familiar with geometric engineering as well. So I won't say a lot about this. Right, so the idea is, so we consider some type 2 string theory. Which takes place on a 10-dimensional space-time. And so what we can do is we can take 6 of these dimensions to be a Claviau threefold, and the other 4 dimensions to be our 4-dimensional Lorentzian space-time. And what we now want to do is we want to make this internal space, this Claviau, we want to make that very small so that effectively we get some description of this string theory as a QFT in these 4 dimensions. And the Claviau threefold, because of its special holonomy, it will tell us that in these 4 dimensions, we are exactly left with a theory that preserves n equals 2 supersymmetry. Moreover, the topology and the geometry of this Claviau threefold, that will determine the field content of this particular QFT. So there are 2 standard ways to geometrically engineer these n equals 2 theories, of which the Seiberg-Witten theory is one example. One way is to do this in 2a, and one way is to do this in 2b. And if we're in the 2b setting, then the Claviau that I want to consider is a so-called Claviau modeled on this Riemann surface sigma. So what does that mean concretely? It means that if this Riemann surface sigma is described by, say, some function into which variables, w and z, in 2 complex variables, then the Claviau, it's a non-compact Claviau, will be described where should I put this? Well, since it's an important equation, let's put it here. Xy plus p w comma z is equal to 0. So how should I think about this Claviau? How should I think about this Claviau? So suppose that we draw this Riemann surface sigma like this. Then at each point which is not on sigma, this p of w comma z gives something which is not equal to 0. And so the fiber at this point is some hyperboloid. Described by the equation x times y is equal to a constant which is not equal to 0. Whereas if I'm on a point of sigma, then this polynomial p, or this function p will be equal to 0, and so the fiber will be degenerate and given by this an equation x comma y is equal to 0. Right, so the sigma, you should think about it as the Seiberg-Witten curve. So this particular geometry is going to engineer a 4-dimensional n equals 2 theory, which has as its Seiberg-Witten curve this Riemann surface sigma. And the Seiberg-Witten 1 form, the differential, that has also a very natural interpretation in terms of this Calabi-Yau, because this Calabi-Yau has a holomorphic 3,0 form, which can be written basically, well, suppose that I call this Seiberg-Witten form lambda, then it can be written in this particular way. And you can show that on this Riemann surface sigma, it indeed localizes to the usual Seiberg-Witten form. So this embeds all n equals 2 theories in string theory. So why is that useful? Well, one of the reasons that it's useful is that it is easier to think about these BPS representations from a string theoretic perspective. Because in string theory, we know that our BPS objects are D-branes. And so there's just one particular kind of D-branes that we're interested in really in this geometry. So there are these 3 branes. We can wrap them around some 3 cycle in x sigma times RT times a time direction. So if you want to geometrically engineer a BPS particle in 4 dimensions, we have to wrap this D3 brane at least along an R, along a line in 4 dimensions, because that's the world line of this particle. And then we have to wrap it around some cycle, which in this case is 3-dimensional, inside of the Calabi-Yau. But this particular configuration is only, well, so this configuration is only BPS when, again, the mass is equal to the absolute value of the central charge. So in this new setting, in this new Calabi-Yau setting, what is this central charge? Well, that's just a straightforward generalization of what we saw in the Seiberg-Witten geometry. So it's a period integral over now this holomorphic 3 form around some cycle gamma. So say, well, sorry. The homology class of L, I should say. And what is the mass of the corresponding object? Well, the mass of this object is just its volume, which in this case is given by the integral over L of its volume. So how do we engineer a BPS particle in 4 dimensions? Well, we engineer a BPS particle by taking this 3 cycle, by deforming it in such a way that this constraint is satisfied. And this is a well-known constraint in geometry. It's a calibration condition. And so it's equivalent to L being special Lagrangian. So in this string theoretic picture, we have a very geometric way of understanding what these BPS states are. Namely, they correspond to these particular branes that wrap some special Lagrangian 3 cycle inside of the Calabi-Yau. And notice that, okay, well, this is maybe something that I should say in detail. So what used to be the moduli space of complex structures on this Riemann surface is now replaced by the moduli space of complex structures on our Calabi-Yau. And obviously, the form of the holomorphic 3 form, it will depend on where we are on this particular moduli space. And so, since this condition, this BPS condition, is formulated entirely in terms of this holomorphic 3 form, so this BPS condition, it depends it depends on where we are on that moduli space. So that's how you see this. Right. Let's see what I want to do in the remaining 10 minutes. So maybe, right, so this is the relevant moduli space of our problem. It's the moduli space of geometric stability conditions because the central charge is really dependent on where we are at that moduli space. So this all reduces as well. Okay, oh wait, sorry, yeah, this is what I want to do. So how can we think about these special Lagrangian 3 cycles inside of these particular Calabi-Yaus which are modeled on a Riemann surface? So this is going to be important as well. So how do these 3 cycles look like? Well, notice that there is a particular S1 in this picture, an S1 which degenerates if we're exactly on top of this Riemann surface sigma, but elsewhere it has a non-zero size. So this is going to be important to realize these 3 cycles, because what we can do now, so let me draw this Riemann surface once more. So suppose we take a 1 cycle, and we know that 4-dimensional BPS states are related to 1 cycles on this Seiberg-Witten curve. But now suppose that, okay, so let's call this 1 cycle gamma, because it will in the end give the electromagnetic charge of the corresponding 4-dimensional particle. But let's now fill it in with something that might be a disk or a generalized disk. Then there will be an S1 at each point, an S1 fiber at each point in the interior of this disk, and that S1, if we go towards the boundary of that disk, it will shrink to 0 size. So we get an S1 vibration over this disk, which shrinks at that boundary. And so if this were really a disk, then this would be a 3 cycle with topology S3. So this is really how we should be thinking of these special Lagrangian cycles inside of this local geometry. There is one more thing that I want to say in order to prepare us for tomorrow. So we had this relation. I want to rephrase this relation in a particular way. So, yeah. So locally, so yeah, let's say rephrase this relation, the BPS relation. So locally, on L, I can always write the 3 form, omega, as just the phase times the volume restricted to L. So here I think of these as forms. So locally, I have this, I can always write down omega in terms of the volume. But what's not guaranteed is that this phase stays constant all over L. So when do we have the equality? If and only if theta, so the BPS equality, if and only this theta is constant. Over L. And this is the condition that is going to be very important tomorrow, where we're going to draw spectral networks. Yeah, maybe one more remark to make this connection to Donaldson-Thomas invariants, as I promised. So remember that we were in the context of 2B, where we had our 10-dimensional background to be this local Calabi-Yau times R 3,1. Now we have a mirror symmetry which relates this to 2a on a different Calabi-Yau where the Hodge numbers are exchanged times R 3,1. And where we had these the 3 branes here, on this side, the branes that we have are D0, D2, D4, and D6s. And Donaldson-Thomas theory originally really started out as a gauge theory that's living on a single D6 brane that is wrapped on this mirror Calabi-Yau. So later it was generalized to include multiple D6 branes. And so the statement is that these generalized Donaldson-Thomas invariants what they're counting is really bound states of these even dimensional branes. And so this geometric engineering picture, this tells us that if we write down a BPS index, so there is a particular index that we can write down in these n=2 theories to count BPS states. And geometric engineering tells us that this should be equal to these DT invariants. So that is basically how these Donaldson-Thomas invariants are going to come in. Maybe I can make one remark about the relation to quivers, although that might become clearer tomorrow as well. So one way to get a quiver is to think about sort of what kind of theory these bound states of these branes, what they result in 3 dimensions. So this will be a 4-dimensional n=1 theory. It will be a theory which has n=1 Lagrangian is described in terms of D terms and F terms. And so that reproduces some moduli space. And that's exactly the moduli space of quiver representations that Marcus introduced us before. I'll make another remark about that tomorrow from the perspective of spectral networks. So I think this is a good point to stop. Are there any questions? Yeah. I can say a little bit about that. So this is called the special helicity index. So basically, if you look at the algebra of the BPS algebra and its representations, then there is one sort of natural object as a trace that you can write down for this algebra, and that is this BPS index that I'm referring to. It's, maybe people can correct me. It's something like this, and then I think there is some J3 coming in, right? So there is some. Is that it? Something like this. Well, and okay, so yeah, there is a particular trace that you can write down in terms of this supersymmetry algebra that can be shown to be an index. It's a Witten, it's a generalized Witten index. Yeah, yes, yes. Any other questions? Yeah, yeah. So yes. So there is a yeah. What shall I say? So so mirror symmetry basically acts on three as T-duality, but three T-dualities. So one way to think about this is to think about these Calabi-Yaus as a three-dimensional real base with a three torus as a fiber. And then mirror symmetry acts as T-dualities on these circles. And so if you think about sort of how these three cycles are special Lagrangian, so this vibration of these three torus is also a special Lagrangian vibration. So if you think about how these three branes are realized in terms of that SYZ vibration, as it's called, and then apply these T-dualities, then that's roughly the picture of the cycles that you find on this geometry, where these even dimensional branes wrap around. Yeah, this is maybe a nice exercise to try for a simple Calabi-Yau. Uh-huh. Yes. Uh-huh. You mean this SYZ picture in that case, or? Uh-huh. Uh-huh. So the uh-huh. 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 Yeah. Yes. If anyone studied that. Well, I don't know that people have made progress in this SYC picture in the mathematical world, because that has always been sort of an obstacle. So is there a geometry that we know sort of, a compact Calabi-Yau geometry that is not too complicated and that we know in enough detail? So uh-huh. That is definitely not something that I've looked into, but yeah, there are people as well who have studied sort of this mirror symmetry between cycles for compact Calabi-Yaus in more detail, which I think is kind of a prerequisite to do any of this, because yeah, basically you need to have a good understanding of the cycles in this compact Calabi-Yau. So I would say that, well, that there's definitely a better understanding mathematically about this nowadays. But I don't know of any physicist who has especially explored sort of these corrections, these gravitational corrections that come from it.